Hey guys, welcome to the video on C-Nmr. Sorry for the long delay in these videos, but I am a little bit sick, so if my voice starts to get a little quieter, just really sorry. You have to bear with me, alright? So, let's get started. So, what is C-Nmr? C-Nmr is just another spectroscopy technique. It just helps us identify it, like our unknown compounds after we've done like a synthesis or something. So, I have a diagram here that you've seen in lecture, right? And it tells you like on the C-Nmr where certain functional groups can be found. And it's always centered around the specific carbon we're talking about, right? C-Nmr is centered around carbons. So you can see the underlying carbon is what we're looking at. All right, so let's just start by going over this. So you can see that everything here, we're looking at sp3 carbons, right? Or actually even more than that. All of this, all right? This is the carbon, 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 all right? And so one key important aspect to know of C-Nmr, is that when you're next to an electronegative atom, you're going to increase your shift. You see, we're getting to higher numbers. All right. So the closer we are to electronegative atoms, the higher up the number is for the shift. This is also called well, it's called shifting, right? But if we are talking about the C-Nmr graph, right, the lower numbers are on the right, high here. So going from right to left, we call that downfield, and now to the right, upfield. All right. So that's one thing to know. So with C-Nmr, there is a important aspect to know, and with H-Nmr too, called unique carbons, right? So what does it mean to be unique? And in this video, I took some questions from your workshop to specifically go through them. I had to wait till after the deadline to be able to use them, but it's going to help us figure out a little bit how to do C-Nmr, all right? So let's go right here. It says, how many peaks would you expect to see in C13 NMR, right, with this compound shown below? So how do we approach this sort of problem? So the C-Nmr is a lot simpler than H-Nmr. All we have to do is look for what we call unique carbons, right? If you've had any experience with H-Nmr, you may be familiar with the concept called splitting. So we don't have splitting in C-Nmr, all right, which makes it a lot easier. So what I'm going to do is I'm going to identify the amount of unique carbons, and that's going to tell us how many peaks we have in our C-Nmr. All right, so let's get started. So let's start with the carbon. Let's start with the methyl carbon, this one. All right. So it's bound to a nitrogen, and so we can say that we have that as one unique carbon. All right. So call that 1. Now look at this one. Is this another unique carbon? Right. Well, is there any difference in that methyl versus this one? Right. Well, it's not. It's bound to the same exact atoms. We're not going to be able. There's no other way we can really tell it's different. Okay. So, and you're maybe thinking, oh, but this is pointing downwards. This is pointing up and to the left, right? Well, remember, single bonds can rotate. So I could have easily just rotated, let's say, a bond, and now we flip that position, right? But remember, it's bound exactly the same way. It's not going to be considered unique. So that's still only one unique carbon. But now let's take a look at these methyls, right? Are they any different from this one? Well, look at them. They're bound to the same nitrogen, right? They're bound to nitrogen, and you can see that the nitrogens, both nitrogens, are bound to the same exact way, right? And why is this? Well, we have symmetry. You can draw a line of symmetry down this way, right? So one of the strategies in C-Nmr and H-Nmr is to draw lines of symmetry, right? It's going to make your job a lot easier. If part of your molecule is symmetrical, you don't need to look at the other part, because on a C-Nmr, it will not show up. Because if we have this methyl, That's one unique one. But this, that's not unique. We're not going to get a separate peak for that. Neither are we for this or this, because they're considered identical. All right? And so we only have one unique carbon still. So I'm going to cross out this one, this one, this one. And you could have just as easily, let's say, marked this one as the unique one and crossed that one out. It's all up to you. But the key thing is the line of symmetry. All right? So let's go to our next carbon. Remember, we're not touching the nitrogen. This is about carbons. So focusing on that carbon. Well, it's not the same as the methyl, right? This one has two hydrogens, right, bound to different carbons. So we can say that that's also a unique carbon. And remember, because of symmetry, since that one is the same, we don't count it, cross it out. So that's 2. And now we're going to just look at that carbon, right? There is no other carbon like that. And so we can say that that is also a unique carbon. All right? So we have 3 unique carbons. And so in your C-Nmr, you're going to get 3. All right? You're going to get 3 peaks. Now, like, what they could look like is like this, like the heights and the positions are inaccurate, but you get what I mean. You'll have 3 distinct peaks, okay? And so that's how that's going to look on a C-Nmr peak, obviously with the shifting in the correct positions and all that, all right? And so that's probably one of the simplest C-Nmr questions you can get. And also, do not think that you can only have one line of symmetry. I think this was a question in the past exam. Hold on. And actually, it might have been in my exam. We were given this structure, all right? And we were asked, how many peaks are we going to get in a C-Nmr, right? And so, how exactly are we going to approach this one, right? Well, remember, first step, line of symmetry. So, I can draw a line of symmetry down the middle, but I can also do it this way. Don't get caught up with the benzene bonds, right? You're thinking, oh, but the 3 bonds in the benzene aren't symmetrical. Well, remember, we can resonate them, so like we can have them like this, or we can have them like this. And because they're always like resonating, we can always draw like that. All right? And so in this case, we have 2 lines of symmetry. So when we're going for our unique carbons, we only need to look at like one quadrant. So I would say that's 1, that's 2. That's 3. And I think that was it. But again, it was similar to the question on my exam, but I may not have drawn the molecule identically, but like the principle is the same as long as you guys get that sort of thing. All right. And so that's another way we have to approach C-Nmr, and just another example for you guys. Okay. So always draw as many lines of symmetry as you can. Now here's another one. Now what they're asking is they gave us a formula and they gave us the C-Nmr, and what they're asking us to do is draw the structure, right? Draw the unknown compound. First thing we have to do for any C-Nmr, H-Nmr question, IHD. Yep, it's coming back in exam 1. So if you don't remember what the IHD formula is, it's going to be 2C plus 2 plus N minus H minus X over 2. Right? You just plug in what you have. So when you plug in everything here, you're going to get our formula, right? We have 2 times 9 plus 2, 0 nitrogens, 18 hydrogens, 0 halogens. X is a halogen. Over 2, okay, that's just going to be, that's going to end up being 1. All right? So that's going to be 1. So what is this going to help us? How does that even help us, right? Well, remember what IHD tells you. IHD can tell you whether or not you have double bonds, triple bonds, rings, stuff like that. So having an IHD of 0 is an alkane, single bonds only. IHD of 1 is a 1 double bond or 1 ring, not both. Having an IHD of 2 can mean 1 double bond, 1 double bond and 1 ring, so both, or 2 double bonds, or 2 rings, or 1 triple bond. And when we get to 3, it just means more of the same, right? So IHD of 1, and that should be one of the first things you ever do in any question of C-Nmr and H-Nmr when they ask you to figure out the structure. So I'll just write it off to the side. IHD equals 1. All right? And so they gave us H-Nmr data, but because this is a C-Nmr video, we're not going to focus on that, and you don't even need it to solve this question. All right? So we're just going to use the C-Nmr. So we have 9 carbons, 18 hydrogens, and an oxygen. Now, when you have an IHD, when you have an oxygen on your compound, right, and you have an IHD of greater than 0, one safe bet is to draw a carbonyl. Carbonyl counts towards your double bond count, which is our 1 IHD. All right, so that's a carbonyl. Yeah, remember there's a carbon right there. Let's just put it in green. So that's one of the carbons, one of the oxygens. So you can see in our C-Nmr, we have 3 peaks. 3 peaks means 3 unique carbons. But in our formula, we have 9. That means we're going to have a lot of symmetry. All right. Remember, C-Nmr does not pick up carbons that are the same. It only picks it up once. All right. So because of symmetry, what I'm going to do to one side, I'm going to do to the other. Right. That may not always help you because the symmetry might be in other places, but it's a good starting point. So let's say I'm going to draw 2 carbons coming off. Right. So far, let's do that in here. So far, we've used one of our unique carbons. That's 1. By adding another carbon, that's 2. So far, we've only used 3 carbons. We have 6 left. But with only 6 carbons left, I somehow can only create 1 more unique carbon. All right? So this is a lot of where the symmetry is going to come into play. All right? So right now, there's only one place that you can put a carbon, and that's like coming off here. Right? If you were to have drawn this, it's the same thing. So you can only do this. That's 3. That means all the other carbons I'm now about to add must be repeats. All right? Well, remember, I can always add another one on the other side. Let me just move this. Right? Remember, it's not going to pick up this one because it's not unique. Right? And so far, all right, 3 unique hydrogens, 3 unique carbons, and we've used 1, 2, 3, 4, 5 carbons. All right? So 4 left. So what if I add 1 there and 1 there? Well, remember, these are just methyl carbons, and it's the same as that. So this methyl is the exact same thing as that methyl. They're attached exactly the same. Those carbons, right? Everything's the same about them. So that's not a unique carbon either. And then that means neither is that one. Okay? We still have 2 carbons left. What if I just added them this way? Well, remember, these are not going to be unique either. None of these 3 are going to be unique from each other. So it's still only going to pick up that 1 the first time. Same deal for all of these 3, right? And so we've only used our 3 unique carbons, right? Because the C-Nmr only had 3 peaks. And we were able to, on the 3rd unique carbon, figure out a way to make 6 of the carbons unique. All right? 6 of the carbons count for 1 unique carbon. So you can see that we got to play into the symmetry here. And so like here, if I draw a line of symmetry this way, 1 carbon, 2, 3, right? Remember, this is the same, and because it's symmetrical, you don't even need to look at this side. All right? And so that's C-Nmr. In the next video, we're going to go into H-Nmr, and then after that, we can go into how to do C-Nmr and H-Nmr together, all right? Because a lot of times they will give you questions that give you both the C-Nmr and H-Nmr spectrums, and they'll ask you to figure out the structure using both, all right? Hope this video helped. Sorry if, again, my voice is a little bit like dragging or, you know, a little bit quiet. I am a little bit sick. But if this helps, if you don't understand something, please go to the CLC or email me. If you're watching this on YouTube, feel free to comment it, and I can answer your questions so others can also see it. And I will see you guys in the next video.